Its heart, making aspirin is all about something called synthesis. And that's really just a fancy scientific term for building a new, more complex molecule from simpler starting materials. We're basically taking a few ingredients and, well, coaxing them into becoming something entirely new.
Now, the specific magic trick we're using here is called acetylation. Honestly, you can just think of it like giving one of our molecules a crucial upgrade. We're surgically attaching a new piece to it, this acetyl group, and this one simple addition is what completely transforms our starting material into aspirin. It's the whole ballgame.
So when you boil it all down, the reaction is basically a simple swap. We start with two main players, salicylic acid, that's our base molecule, and acetic anhydride, which is the chemical that's going to donate that all-important acetyl group. When they react, the salicylic acid gets its upgrade and becomes acetyl salicylic acid, which is just the full chemical name for aspirin. And the leftover bits, they form a pretty familiar byproduct, acetic acid. You probably know it better as vinegar.
Okay, so how does this actually play out in a lab? Well, it's a lot like following a recipe, really, just with beakers and flasks instead of mixing bowls. The entire process can be broken down into 4 key steps.
First up, we combine our main ingredients with a little something called a catalyst to get things going. Second, we add some gentle heat, which gives the molecules the energy they need to actually react with each other. Now, the third step is honestly the most dramatic. We take the warm mixture and pour it straight into ice water. This sudden temperature shock forces the brand new aspirin molecules to literally crash out of the liquid and form solid crystals. And finally, all we need to do is collect them, usually by filtering out all that leftover liquid.
But here's the thing. Those crystals you get from that first step, they are definitely not ready to be put in a bottle. They're what chemists call crude, which is just a way of saying they're still mixed up with impurities, like that leftover vinegar. And believe me, when it comes to medicine, purity is everything.
This really is the core principle of all pharmaceutical chemistry. Getting rid of those unwanted side products and any leftover ingredients is absolutely critical. It's what makes a drug both safe and effective.
So, how in the world do you clean up these tiny little crystals? Well, the most common method is a beautiful process called recrystallization. The idea is simple. You dissolve the crude aspirin in a hot liquid. Then, and this is the key part, you let that liquid cool down slowly. As it cools, the pure aspirin molecules have time to find each other and neatly arrange themselves into perfect, clean crystals, which effectively pushes all the impurities out to be left behind in the liquid.
All right, so we've seen the lab steps, the mixing, the heating, the cooling, but what's really happening on a level that's totally invisible to us? Let's zoom way in on the molecules themselves and see how this transformation actually works.
This is where the chemistry gets really elegant. It's not random at all. It's more like a precise 3-act play where atoms and electrons are moving in this perfectly choreographed sequence.
Act 1. The attack. An oxygen atom sitting on the salicylic acid molecule is very attracted to a carbon atom on the acetic anhydride, so it uses its electrons to reach out and form a new bond, and that one move kicks off the entire process. In Act 2, this attack fuses the two molecules together, creating this new temporary structure. Now, chemists have a name for it, a tetrahedral intermediate, but you can just think of it as this awkward, unstable halfway point. It's a structure that just can't stay that way for long.
And that brings us to Act 3, the collapse. That unstable intermediate quickly breaks apart, but not the same way it came together. It kicks out a different piece, which becomes our acetic acid byproduct. And what's left behind? Our target, a perfectly stable aspirin molecule, now with that new acetyl group attached for good. The swap is complete.
But hang on, remember those few drops of phosphoric acid we added way back in step 1? That's our catalyst, and it plays the role of a kind of chemical matchmaker. It doesn't actually become part of the final aspirin molecule at all. Instead, it just speeds the whole reaction up by helping our two main ingredients connect more easily. It's a crucial helper that makes things happen, and then it just leaves totally unchanged.
So, after all that work, the reacting, the purifying, how does a chemist know if they've actually made pure aspirin? You can't just eyeball it. They have to run tests. They have to give the final product its final exam. You see, every pure substance has a unique chemical fingerprint, and for aspirin, one of its key identifiers is its melting point. Pure aspirin melts at a very sharp, very consistent 135 degrees Celsius. Any impurities will mess up its perfect crystal structure, and that causes it to melt at a lower, less precise temperature. It's a simple test, but it's an incredibly powerful quality check.
And the difference is something you can literally see,
smell, and measure. Pure aspirin, it should be clean, odorless white crystals with that sharp melting point. An impure product, though, might still have that faint smell of vinegar, it could look a little discolored, and its melting point will be kind of mushy and lower than our 135-degree target. All of those are dead giveaways that more purification is needed.
And really, that vinegar smell is the biggest tell. It comes directly from that acetic acid byproduct we tried so hard to wash away. So if your final product is completely odorless, that's a fantastic first sign that you've done the job right. It shows that sometimes your own nose can be a pretty powerful tool in the lab. So there you have it, from a simple swap of molecular parts to a precise recipe of heating, cooling, and purifying. We've just unpacked the entire hidden chemistry inside one of the world's most common pills. It kind of makes you wonder, doesn't it? What other incredible chemical stories are just sitting there waiting to be told right in your own home?